This is Geometry Lessons 6.4 Types of Quadrilaterals. The big idea says the most common special types of quadrilaterals are related to each other in a hierarchy that helps in sorting their properties. So in this section, we're just going to be classifying different types of quadrilaterals and identifying specifically what is special about each one and then how they're related. Um, our final goal, if you take a look at the back, is to relate all of these in a hierarchy. So this is our hierarchy here with quadrilateral at the top. So everything underneath of that is a special type of quadrilateral. So everything we talk about today is a quadrilateral. And the most specific type is a square, as you can see. And everything is going to follow up to quadrilateral. So that's our end goal. We're going to kind of work our way down the hierarchy and explain each one individually. So we're going to start with the parallelogram family. These are the ones that you've probably dealt with the most just through your basic pre-algebra and algebra. So our parallelogram is any quadrilateral. So first of all, let's not forget quad means four. That's why when you ride a four-wheeler, sometimes you'll hear it called a quad, four. So when you see quadrilateral, four-sided shape. So a four-sided shape is a parallelogram specifically only if both pairs of its opposite sides are parallel. So not just one set of opposite parallel sides, but two sets of opposite parallel sides. So you'll notice that they have these little arrows. That means parallel. So DC is parallel to AB, and then AD is also parallel to BC. Notice how this one has two arrows and these have one. That's just to show the difference between the two distinct pairs. So if these are showing two and there was another line somewhere else that also had two, that line would be parallel to these specifically. We couldn't put just one arrow on all of them because they're not all parallel to each other, right? These are parallel to each other, so we did it with one arrow. These are parallel to each other. You could have done three. It doesn't matter. It just needs to be a distinct amount of arrows so that we know which ones are parallel to which. So two pairs of opposite sides is a parallelogram. Let's move over to a rhombus. Four-sided shape is a rhombus if it has four congruent or equal sides. So any four-sided shape that has four equal sides is considered a rhombus. Now, this is where a lot of students start to get confused because they've always thought of a shape with four equal sides as a square. But you'll notice this shape here does not have 90-degree angles. It's not a square, it's just a rhombus. And when we get to square, you'll see it's a type of rhombus. So every square is a rhombus because it has four equal sides. Okay, but if it's just a four-sided shape with four equal sides and there's nothing special about the angles, okay, we would just consider that a rhombus. Okay, and then a rectangle has to do with the angles specifically, not the sides. Quadrilateral is a rectangle if and only if it has four right angles. So any four-sided shape with four right angles or 90-degree angles is a rectangle. And then that brings us to our square, which is a combination of both of these. Quadrilateral is a square if and only if it has four congruent sides and four right angles. So if it's a rectangle and a rhombus, four equal sides, four 90-degree angles, then it is a square. So just like we were talking about, if we look at this Venn diagram, notice how the entire circle that represents all squares is inside the bigger circle that represents all rhombuses. So you theoretically could pick a square from anywhere inside the circle and it's still inside the bigger set of rhombuses. So every square is a type of rhombus. But there are rhombuses out here that we could choose that while it's a rhombus and has four equal sides, it does not fall into the specific category of a square because it does not have four 90-degree angles. And so here's a little snippet of the hierarchy that we have so far. Notice all of these, although it wasn't specifically stated here in the definitions, they all fall underneath parallelogram. If you look at these shapes, opposite sides here, we could put the arrows on it, of a rectangle, they're parallel. These are parallel to this one. The same is true in a square. Since it's a rectangle, that has to be true. And then the same thing is true up here. This side's parallel to this side's parallel to this. So a rhombus, a rectangle, a square, they're all parallelograms, so they fall underneath that kind of in this tree. So parallelograms can be split into rhombuses, all equal sides, rectangles, 4 90-degree angles. And if I have a combination of both of those, then that is a square. So those are the most common ones that we talk about. So let's get into two different types that are not quite as common. So starting with kites. So you probably haven't studied kites until now. You may have seen shapes that look like a kite, but you haven't specifically talked about what's special about their properties, like you probably already have with rectangles and squares. Okay, so a kite, fifth type of quadrilateral that we're going to look at, it's formed by the union or the combination of two isosceles triangles. So if you take a look at this shape right here, I've got this isosceles triangle up here, which means this side equals this side of triangle ABC. That's an isosceles triangle. Combined, so that's the union, means combined, with this triangle ACD. These sides are equal to these sides. Not necessarily equal to these, it's its own isosceles triangle, with the bases removed. Right, so we've got this triangle, and that's why there's a dotted line here. So it's not actually part of the shape. The outer shape here, which is the combination of this little isosceles triangle and this bigger isosceles triangle, okay, together, if we remove the base, that is a kite. Now, this results in two different looking shapes. One that actually looks like a kite that you would fly, right, in the air. It looks like a kite, so that makes sense. But this shape over here, notice the dotted line is not part of it. So take that out. It's this shape here, where they're going to refer to it as an arrowhead or a dart. This is also a kite because we've got our big isosceles triangle. If you look at it, it's ABC. So this side equals this side. And then we have our smaller isosceles triangle right here, where these two sides are going to be equal. And then the bases are removed. They share the same base, but it's removed. And that gives us this shape that looks kind of like a dart or an arrowhead. That's also considered a kite. So the definition of a kite, to get very specific now, it's quadrilateral and it has two distinct pairs of consecutive sides that are the same length. Okay, so let's look at an example of one that has consecutive sides that are the same length, two pairs of them but not distinct. That would be right here. And this is all going to be explained in this paragraph, but I'm just going to kind of talk through it here in the pictures and not read it to you. So this shape right here, first of all, consecutive sides means as you make your way either clockwise or counterclockwise around the outside of your shape, we go from one to the next. We've talked about that means consecutive. Consecutive angles would be B and A or B and C, because as I make my way around, right, I hit those as I go around the circle. So consecutive sides is the same thing. As I make my way around, they're next to each other, basically. So this one, we want to make sure we understand why this does not fit the definition of a kite. I have one pair of consecutive sides that are equal to each other right here. And I have another pair of consecutive sides that are equal to each other right here. So if I didn't have this word distinct in the definition, I could call this a kite. The reason I cannot call this a kite is because I do not have two distinct pairs. These two pairs of sides share EF, right? This pair of sides are equal, this pair of sides are equal, but each one of those pairs is using EF as part of it, and that's why it's not a kite. So to be a kite, these would have to be equal to each other, and then there'd have to be another separate or distinct pair of sides that were equal to each other. So this actually looks to be a trapezoid, which we're going to talk about on the back. We only know that, though, if there are certain parallel sides. And we'll talk about that in a second. So this is not a kite. Let's make sure we understand that. If you look back at this, that is not a kite because it does not have two distinct pairs of consecutive sides. And look at this shape right here. This is a rhombus, right? 4 equal sides. So you might say, well, that's not a kite. But as I work my way around, I have a pair of consecutive sides that are congruent right here. And I have another distinct separate pair. They're not sharing any of the sides from this pair down here. So this is a rhombus, but this is also a kite. It has two distinct pairs. Think about it as the original definition we talked about up there. It's an isosceles triangle combined with another isosceles triangle with the base removed. Okay, so what I've also shown you now is that a rhombus can be a kite, or actually it is a kite. A rhombus is a kite. Every rhombus we look at, if we slide back up here, has two distinct pairs of consecutive sides that are congruent to each other. So a rhombus is a kite, which means a square is a kite as well. So this can get confusing because squares and rhombuses are parallelograms, and they're also kites. And then there are kites that are none of these, and there are parallelograms that are none of these. And so you can see that's why we spend a whole section just on the classifications of these things, because it can be a little confusing trying to keep them all straight. Okay, so there is our kite. If you flip it over, the last one we're going to look at is our trapezoid family. So the definition of a trapezoid, quadrilateral, four-sided shape, has at least, and that's important, at least, meaning it can have more than one, so at least one pair of parallel sides. So here's your basic looking trapezoid, has one pair of parallel sides, the other one is not. But since it says at least, that means it can have two pairs of parallel sides, where if you look right here, this has two pairs of parallel sides, so that's a parallelogram, right? But if it has at least one pair of parallel sides, then it's also a trapezoid. So I can call this a trapezoid as well. So let's dive a little deeper. Parallel sides of the trapezoid are called the bases. So your basic trapezoid that isn't also a parallelogram or something else, like we see right here, just has one set of parallel sides, and those are going to be called the bases. So this one and this one are the bases because it's the actual parallel sides. If we have a parallelogram like this that's also a trapezoid, you can call these the bases or you can call these the bases. It actually has two sets of bases, and it'll get into that in here. I'm not going to read all that to you. Now, we talk about base angles, which are the vertices that are at the endpoints of these bases. So here's a base right here, endpoint of A and B. Those would be considered base angles, and that's what it explains right here, A and B. And then up here we have this other base, so C and D would be base angles. So that's pretty simple. Find the two sides of the base. Those are considered base angles. Two sides of this base, those are considered base angles. So what's not a base angle? A and D are not because they are not the endpoints of a base. This side of the four-sided shape is not considered a base because it's not parallel to the other side. So its endpoints are not base angles. All right, so it kind of talks about, if you read through all of this, how this has two sets of bases. So I've got base angles of K and M. I've got base angles of J and L. And if I consider the other sides the base, which I can because they're parallel, then J and K are base angles and L and M. So that's a very specific case. We're really not going to look at those too much. We're mostly, if we're looking at trapezoids, going to be looking at one pair of parallel sides. Those would be the bases. So H and E are your base angles. And then G and F on opposite sides of this base down here. Those are also base angles. Now, those are not necessarily equal to each other, so we want to be careful when we mark those like that. They can be, and that's what we're going to look at right here with an isosceles trapezoid. But in a regular old trapezoid, D and C are base angles, but they are not equal to each other. They're only equal to each other in one specific case, and that is your isosceles trapezoid. So a trapezoid is an isosceles trapezoid if and only if it has a pair of base angles equal in measure. That's what we just looked at. So if we look at this trapezoid, I know it's a trapezoid because it has at least one pair of parallel sides. AB is parallel to CD, so therefore it's a trapezoid. And it's been marked that these two angles are equal to each other, which means this is an isosceles trapezoid. And it doesn't specifically go into this in the chapter, but if these angles are equal, these two angles are going to be equal to each other, not equal to these, but equal to each other. And it also creates sides that are equal to each other. So if I come over here, I automatically know this side's equal to this side because I see those angles equal to each other. I also know these angles, these other base angles, will be equal to each other. Okay, so because a rectangle has opposite sides parallel and all angles congruent, every rectangle is an isosceles trapezoid. Read that again. A rectangle has opposite sides parallel, and then all the angles are congruent, meaning it has base angles that are congruent. It has parallel sides, which makes it a trapezoid, and all the angles are congruent, so that means the two base angles are congruent to each other. So therefore, every rectangle is an isosceles trapezoid. So as I start to relate these, we look at these hierarchies. Quadrilateral at the top just means four sides. A kite, remember, has two distinct consecutive sides that are equal to each other. A trapezoid, we're talking about parallel sides, has at least one pair of parallel sides. If it has two pairs of parallel sides, that trapezoid is now a parallelogram, still a trapezoid, still a quadrilateral. Okay, everything that you see above it is still true. Not everything below it is necessarily true. It could be true. Okay, and a special type of trapezoid is an isosceles trapezoid. Can it also be a parallelogram at the same time? Yes, that would make it a rectangle. So if it has base angles that are equal and two pairs of parallel sides, then we are going to have ourselves a rectangle. So it falls under all of this. And then, of course, we understand how a square relates to a rectangle. We can also go down the kite side. A rhombus is where these two things start to come together. So a rhombus we talked about is a kite because it has two distinct consecutive sides, pairs of consecutive sides that are equal. Okay, it also has at least one pair of parallel sides, so that makes it a trapezoid, and it has two pairs of parallel sides, so it's also a parallelogram. And then the picture on the right is exactly the same as the one on the left, just with the shapes, so it's a little bit easier to identify what each one is if you forget kind of what they look like. And then this theorem just basically says that if you follow your way up the hierarchy, everything that's down at the bottom, it shares the properties of everything above it. So if I know something is a square, all the special properties of an isosceles trapezoid and a rectangle and a trapezoid and a quadrilateral and a parallelogram and a rhombus and a kite, they all have to be true for a square. A square is a kite. A square is a parallelogram. A square is a trapezoid. So all the things that make these special are all true about a square. If I come up to a rhombus, it shares everything for a kite, a parallelogram, a trapezoid. It does not necessarily have all of the properties of a rectangle. If it did, we'd call it a square. Okay, so you can follow this up, and everything that's above a shape, all of those properties are true for that shape. And that's what the quadrilateral hierarchy theorem says.